there's a plausible argument that there isn't anybody out there, bearing in mind that we can be wrong, we ought to keep looking, because the question is of the most supreme importance. It calibrates our place in the universe. It tells us who we are. And so it is worthwhile trying to find other civilizations, I would say, no matter what.
Earth is extraordinary, from vast blue oceans to tall snow-capped mountains. Most distinctly, though, our big blue planet is thriving with life. When we look up to the night sky full of billions of stars, it's hard not to wonder what else could be out there. Does life exist somewhere else in the universe? For 2,000 years, this has remained the most compelling question of mankind. And guess what? The answer is a lot closer than you think. Our solar system is made up of 8 planets, all of which orbit around the Sun. The smallest planet in our solar system, Mercury, is also the closest to the Sun. Then Venus, Earth, Mars, Jupiter, Saturn, Uranus, and lastly Neptune. The first 4, the ones closest to the Sun, are considered terrestrial planets because they are primarily composed of silicates and metals, having distinct metallic cores. The latter 4 are called the Jovian planets, or the gas giants. They are characteristically much larger than the terrestrial planets and are primarily composed of hydrogen and helium with no solid surface. The gas giants are massive and thus have an extremely high gravitational pull. Since they have such high gravity, they are more likely to have more satellite bodies, or moons, orbiting them. More specifically, Jupiter has 79 moons, Saturn has 62 moons, Uranus has 27 moons, and Neptune has 14 moons. Gravity from the parent planet effectively heats the orbiting bodies and sparks a gravitational energy which shapes the moons into round bodies, similar to the process for planets. The gas giants are much further away from the Sun, which causes them to be extremely cold. In the hunt to find life elsewhere in the universe, icy moons orbiting the gas giants have shown great potential to have the necessary ingredients for life to exist. NASA flyby missions Voyager 1, Voyager 2, Galileo, and Cassini studied the moons of Jupiter and Saturn, specifically Europa, Ganymede, and Enceladus. These moons are all covered in ice. However, they show strong evidence for liquid subsurface oceans beneath the ice. Life is thought to have originated in oceans on Earth. Therefore, if these moons have subsurface oceans, they might also have life existing within them. Europa is a small moon of Jupiter, only 1/4 the diameter of Earth. Like our planet, the icy moon is thought to have an iron core surrounded by a rocky mantle predominantly composed of silicates. The surface of Europa is considered a floating icy shell, approximately 15 to 25 kilometers thick, which insulates an underlying ocean of liquid water approximately 60 to 150 kilometers thick. The icy surface is considered to be ice 1 rather than a high-pressure polymorph. We believe Europa's atmosphere might contain water being actively emitted into space from plumes and runaway tidal heating. Tidal heating or dissipation of the icy shell is highly dependent on the gravitational interaction between the ocean world, other moons, and their parent planet. Using spectroscopy imaging from flyby missions Cassini and Galileo, we've determined that its smooth icy surface is relatively young and has been shaped by resurfacing in current geological activity, which implies that the interior of the satellite is warm from heating, thus could potentially have and sustain subsurface liquid water. Surface features on Europa include craters, ridges, cycloids, hotspots, plumes, triple bands, and dark spots. These physical geologic signatures are results of chaotic tectonics, tidal forces and dissipation, and radiogenic heating, which suggests less viscous material is beneath the surface. The largest moon in our solar system, Ganymede, also orbits the planet Jupiter and is another candidate for harboring life in its subsurface oceans. Ganymede is completely differentiated like Earth's interior, although the different layers vary in thickness and composition. It is composed of a solid iron inner core, liquid iron and iron sulfide outer core, silicate mantle, and icy crust that insulates the underlying layers. There is evidence that Ganymede has a magnetic field, likely due to its metallic core, making it the only moon with a magnetic field in our solar system. Between its icy surface and the rocky mantle, there is evidence for a liquid water ocean based on the observations of its auroral ovals by the Hubble Space Telescope and observations of its magnetic field by the Galileo satellite. Saturn's moon Enceladus is not only the brightest satellite in our solar system, but also constitutes properties and characteristics of a subsurface ocean which could be habitable by life. Its icy surface is dominated by plumes located at the south pole of Enceladus, which erupt water vapor and salty ice particles. The surface is entirely covered by ice and is considered to be geologically active. Silicon-rich nanoparticles have been discovered on the moon, which suggest hydrothermal interactions in subsurface water. The orbital eccentricity is high enough to heat the moon and sustain subsurface liquid oceans. The Cassini mission not only discovered subsurface oceans on the Jovian satellites, but also geological signatures of cryovolcanism. Cryovolcanic activity and ice tectonism are responsible for the resurfacing of Europa and Enceladus. The spacecraft determined through in situ sampling of plumes that Enceladus is 90% water vapor, and the other 10% is composed primarily of propane, methane, carbon monoxide, nitrogen, carbon dioxide, and other icy particles. Cryovolcanism is also present on Ganymede, as seen by the bright, young, icy surface and craters which have been relatively smoothed out. Geologically, Ganymede is considered one of the most complex objects in our solar system, with mysterious, strikingly opposing geological features. 1/3 is considered dark terrain that is heavily cratered, and the other 2/3 is bright, icy, smooth, grooved terrain. Ganymede is the only object in our solar system that has an internal magnetic field, which is evidence for a liquid iron core. Effects of an induced magnetic field also suggest subsurface liquid water. The shifts in terrain and presence of a magnetic field suggest cryovolcanism, tectonics, and radiogenic heating have been at work on Ganymede in the past. Science has come a long way since the Voyager, Galileo, and Cassini missions, but there are still many questions that need answers. The NASA Outer Planet Assessments Group has designated a group specifically for the exploration of these satellites called the Roadmaps to Ocean Worlds. ROE has already started asking questions and preparing how to find the answers using satellite-launched flybys, landers, and crawlers. The Clipper mission's main objective is to determine the habitability of Europa using a lander to probe and analyze the landscape. The mission will take remote sensing surveys, mapping, and radar probes to conduct in situ analysis to confirm the presence of a subsurface ocean while profiling the surface of Europa. The Jupiter Icy Moons Explorer mission, better known as JUICE, will explore moons of Jupiter, including Europa and Ganymede. The satellite will orbit Ganymede for 8 months with these main objectives: measure the icy shell thickness, determine the transition zone between ice and water, and map the magnetic fields. This mission will give us insight as to how the moon formed, what geologic processes are occurring, if there is a subsurface ocean, and identify the complex surface of Ganymede. The Cassini mission already determined the habitability and established the area most ideal for a lander on Enceladus, the Tiger Stripes. Therefore, the largest objection for the next mission to Enceladus would be to search for life. The Enceladus Lifefinder mission, or ELF, would primarily focus on 3 objectives: evolution, habitability, and life, to search for the sources and locations of organic synthesis, to determine if those areas with organic compounds are a suitable habitat for life, and find if life already exists in those areas with organic compounds. Europa, Ganymede, and Enceladus exhibit significant geophysical evidence for subsurface oceans, which are influenced by the gravity of other moons and their parent planets Jupiter and Saturn. Geological processes such as tectonics, cryovolcanism, radiogenic and tidal heating have been observed on the Jovian planets and confirm the presence of liquid water beneath their icy surfaces. Evidence for these subsurface oceans has largely come from the Cassini mission, but future missions have been thoughtfully planned in order to obtain more relevant data and information on these moons to determine their habitability or a presence of life within our solar system. Future missions set to explore these ocean worlds hold the key to determining if there is a habitable environment for life in our solar system, and if life is already growing there.
As human beings, we are constantly asking questions. Who am I? Why are we here? What is the meaning of existence? But it turns out, the big question for life is, are there other worlds out there? Is anything living on them? Looking up at all those points of light, we'll always wonder, is there life out there somewhere?